Hello friends, in this lecture I would like to explain another example based on the two-way slab. See here, design a two-way slab for a room 4000 mm by 3500 mm clear inside. If the superimposed load is 3 kN per meter square and floor finish is 1 kN per meter square. Use M20 grade concrete and Fe 415 HYSD bars. First take down the given data. What is given in the question? So your shorter span, which is Lx, will be equal to 3500 and Ly will be equal to 4000 in mm, and live load will be equal to 3 kN per meter square. Floor finish will be equal to 1 kN per meter square, and FCK will be equal to 20 Newton per mm square, and Fi will be equal to 450 Newton per mm square. So in the one-way slab, so by seeing the data itself, first you can make it confirm whether it will comes under one-way slab or two-way slab, then go to the design. But in the two-way slab, there will be various conditions we have to observe. So what are the various conditions? First, each and every time we can go with the ratio Ly by Lx. Whether it will be less than or equal to 2 comes under the two-way slab. There will be one confirmation, it will comes under the two-way slab. It will be greater than 2, which comes under the one-way slab. Okay, so what is longer span direction, which is 4000 by 3500? If you see how much the ratio will be, so the ratio will be around 1.14, which will be less than 2 only. So therefore what happens, the design comes under the two-way slab. So here in the question sometimes they will ask directly design a slab. At that time you can check the ratio first, so whether it will comes under two-way slab or one-way slab. After that, here what they are given that, so they will given the data will be shorter span direction will be some 3500, which was in x direction, and in the y direction it will be around 4000. So here they didn't mention any conditions. Why? Because in the same problem I will explain different conditions. What are the different conditions in the two-way slab? So simply supported slabs means there will be no continuous edges like this. So restrained slabs means it has continuous edges. Continuous edges means continuous edges on one side, two side, three side, four side. For example, if you see this is slab here, and again if I will take one more slab here, so we are going to design this particular slab dimensions of some 4 by 3.5 in meters. So here one edge will be continuous. Sometime the condition will be different. Two edges will be continuous, means these two adjacent edges will be continuous. Sometimes opposite edges. So this is the span what we are designing. So on the continuous edges will be like opposite sides, like this. Either in long span direction, long span edges continuous or short span edges continuous. Like the span is continuous in different ways. That is another type of movement conditions what we have to take. First, we will go with this condition. The slab is discontinuous on all edges and it will be prevented from lifting. So why? Because another thing what we have to see clearly observe means, so this is the top view what we are seeing now. For example, if I take the same slab in 3D mode, so this is the slab of some 3.5 meters by 4 meters. So the slab has rested on the columns like this. So if you observe here, what happens, this is a simply supported slab and there will be no continuous edges, which is discontinuous on all sides. At the time what happened, so you know the condition, one way slab, this is one way slab means x direction, longer span direction, shorter span direction. So in the one way slab, this one way slab bends in shorter span direction. Therefore we are providing main reinforcement in shorter span direction and distribution reinforcement in longer span direction. So this is the distribution reinforcement and this is the main reinforcement. But coming to the two-way slab, two-way slab bends in both the direction, either in y direction and in x direction. Therefore, we have to provide main reinforcement in shorter span direction and longer span direction. Then there is a chances of bending the span in both y direction and x direction. Therefore, we have to provide reinforcement on both the direction. At the same time, if the slab is continuous like this, if the slab is continuous like this, what happens? For example, see here, the slab is discontinuous on all edges. So whenever a load will be, so therefore maximum bending due to torsion moment, the corners will have a chance lifting up like this. So this is the slab which is simply supported and discontinuous on all the edges. So here there is a chances of lifting these corners up, because whenever maximum load is applied on the span, exactly maximum load will be applied at the center only. We know that condition. So at that time what happens? There is a chances of lifting up these corners. You assume that any paper, so if you apply any load on the paper, what happens? Automatically its corners will be lifted up because there will be no weight at these papers. Again, if you apply some weight here on the edges of the paper and you apply load, means what happens? There will be no lifting up these corners. In the same way, the corners of the slab also restrained by providing torsion reinforcement. For example, if we provide some torsion reinforcement here based on its calculation at its edges on four sides, automatically it can be prevented from lifting. Therefore, designing the slab only for the simply supported slab conditions. So if we have to prevent from lifting, we have to provide reinforcement, means we are giving some extra weightage at the corners such that it cannot lift at its corners. And so only these conditions happens in the simply supported edges only. And one more thing what you have to observe, if the slab will be continuous like this. So if you see this case, the slab will be continuous on adjacent edges. So this is one edge, this is another edge. So what happens here? This corner cannot lift up. Why? Because there is continuous this slab. So the reinforcement also providing continuously from here to here like this in the slabs. Therefore, there is no chance of lifting up here. And coming to this corner, this is a free corner and there will be no continuous edges on both ends. So automatically this corner will lift up here. That is the reason we have to provide torsion reinforcement at this corner. Torsion reinforcement at this corner. So for that, what is the percentage? We have to provide some 3/4 area of the steel like that. I will explain in the calculation how you have to provide. And coming to these two edges, this edge and this edge, one edge it will be continuous, another edge it will be free. Therefore, we have to provide half of the reinforcement what we have to provide at the free corners, which is 1/2 means 3/8 area of the steel. Here also the same condition will be happens. Why? Because up to some extent it will be preventing from other edges. So other edge it will be free. Therefore, we have to provide half of the reinforcement at these two corners. So we have to provide full reinforcement at these corners, and here no reinforcement is required. So come to this condition. So this slab will be continuous on opposite edges. So both are the opposite edges. At these edges what happens? See here, there will be half of the reinforcement comes from these corners, and at the same time each and every side of the corner, this will be discontinue and this will be continue, discontinue, continue, discontinue, here continue, discontinuous edge and continue edges. Means here we have to provide just half of the reinforcement for all the corners of the slab. Here also four sides. For example, if you see a slab consists of three edges continuous like this, at that time what you have to do means we have to provide half of the reinforcement at these two corners, 3/8 times, 3/8 times, and here no reinforcement is required, no torsion reinforcement is required. For example, if the slab will be continuous on all edges, so at that time no torsion reinforcement is required. So here no torsion reinforcement required. So like that the slabs will be different types. You have to observe in the two-way slabs. So first, according to our question, there will be no conditions. Just I am solving the problem based on the simply supported conditions. Again, I will show how to provide torsion reinforcement. Again, I will take the condition. If the edges will be continuous, in what way how to solve the problem. Like that, in this one example itself, I will show the difference of the three examples. Then coming to this problem, so I will go for the continuation of the problem. So our first step always what we have to remember, check the L by D ratio. So that L by D ratio also based on the, so I am preferring depth of the slab. So our first step is based on the L by D ratio, span to depth ratio. So how much it will be? For that you can observe in the code book page number 39 in IS 456. So check that page number where it will be. So 415. See here in the page number 39, you read once, for slabs spanning in two direction, that is two-way slabs. The shorter span of the two spans should be used for calculating the span of the effective depth ratio. For two-way slabs of shorter span up to 3.5 meters. So our LX will be 3.5 meters only. So we will suit this condition. With mild steel reinforcement, the span to overall depth means L by capital D, not small d. Ratios given below may be generally be assumed to satisfy vertical deflection limits for loading class up to 3 kN per meter square. So live load up to 3 kN per meter square. And simply supported slabs L by D ratio will be 35. And that too what they are mentioned, this is for mild steel, which is we are using Fe250. And for HYSD bars, you can take down the factor as multiplied by 0.8 for these values. For continuous also it will be 0.8. So 35 into 0.8. How much it will be? It will be around, so if you cross check with your calculators, 35 into 80, how much you will get? So around you will get some 28, L by 28. So L by D will be equal to 28. So depth ratio will be around L by D. So this is how the L by D ratio we have to take in the slabs. So this is capital D here. I will take capital D only, and that too capital D will be around 28. So check with the depth. Take down L value in the shorter span direction. This is 3500, 3500 by 28. So you will get around 125 in mm. So your overall depth will be 125 mm. See here, I will take approximation of capital D will be equal to some 150 mm. So approximate value, and small d I will choose effective cover around some 25 mm. So small d I will take 125 mm. So based on this condition, we will get one conclusion. So it does not less than 125. So your capital D we cannot provide 120 and less than that value. Why? Because the base value will be 125 here. I will do somewhat extra for resisting the bending moment purpose. And again later we will check whether it will suits the depth. Otherwise we can change the depth based on the deflection control and movement depth required. So I will adapt these values for effective depth purpose and overall depth purpose. Then our next step is, after obtain these values, our next step is preferring the effective span here. Effective span. So we know the conditions for the effective span. So what is the condition? We know clear span plus effective depth. So I will take both in x direction and y direction. So LEX, which is in x direction, clear span will be 3500, effective span will be 125. How much you will get? 3625 in mm. And in y direction 4000 plus 125. So approximately we will get 4125 mm. So this is the ranges for the shorter span direction and longer span direction. And again check the ratio of LEY by LEX. So you will get same only 4.125 by 3.625, almost you will get 1.14 mm only. Then you can go for the next step, which is slabs. Loads. So for slabs, so already we know that This is the slab portion, and the thickness is how much we choose here. It will be d will be equal to 115 mm. So this is the depth of the slab what we provided. And in the short span direction, lengthwise it will be around lx wise it will be around some 3625 in mm, and in the long span direction, so it will be like this, around some 4125 in mm, both directions. So this is the slab and the depth of the slab. So how the loads will be calculated? Self weight of slab, that one will be equal to, see here, d into, here generally for the beams what we are taking here, b into d into unit weight of the, for unit meter we are taking into its unit weight. But for slabs, in the lengthwise it will be 3.625, in the widthwise it will be 3.65. Therefore what I am taking here, in the lengthwise I will take some up to 1 meter, in the widthwise also I will take up to 1 meter. So totally it is in meter square. Okay, that is 1 into 1 into unit weight of RCC is 25 kilonewton per meter cube. So if you simplify, d will be 0.15 in meters. If you simplify, how much you will get? You will get around, you will get around 3.75 kilonewton. So here meter and meter cube will be cancelled, but we are taking up to 1 unit meter square both in one direction and one direction. So slabs always calculating in meter square, for beams only meter. Therefore for beams it will be kilonewton per meter, for slabs it will be kilonewton per meter square. You please observe the difference here. And at the same time, each and every live load you observe in the question, they are given 3 kilonewton per meter square, like that. For beams it will be given 3 kilonewton per meter only, and again floor finish will be given 1 kilonewton per meter square, otherwise you can assume your own value. So then take down the total load, 3 plus 1 plus 3.75, so which is 7.75 kilonewton per meter square. Again take down the factor load, which is 1.5 times of 7.75, that one will be around 11.625 kilonewton per meter square. So this is the loads how we have to calculate it. So the total load will be around 11.625 kilonewton per meter square. Then after this we have to go for next step, finding moments based on the loads, moments. So for one way slab, generally what we have to do, we are finding directly. Before going to the moments, check whether this depth will be suitable for this span or not. So depth will be find out based on the moments only. First check with the moments and then we will find for the depth. So how the moments will be find for the two-way slabs. So see in the book page number. So the table is 27. So this is the table in the IS page number 91, table number 27, bending moment coefficients for span, spanning in two directions at right angles, simply supported on four edges. So here our condition is simply supported on four edges, means there will be no continuous slabs. If the slab is continuous, we can go for another table which was in page number 26. After completion of this problem, again I will come and I will discuss what are the conditions here. First I will the simply supported conditions. So here if the slab is simply supported on four sides, you can check with these conditions. Your Ly by Lx ratio will be 1.14. So here you will get the coefficients alpha x and alpha y. After that we have to substitute the same values with the mx will be equal to this alpha x value what we chosen here, and w we use the ultimate load what we calculated here, that is 11.625 kilonewton meters, and lx is the short span direction. For both my also you will get, for mx also you will get lx. So this was in is 456. You can take down the formulas as it is, and here you have to choose alpha x and alpha y. So generally the value is 1.14. So there will be values for 1.1 and 1.2. So we want exact values of 1.14. So if you want exact values of 1.14, what we have to do? We have to go for interpolation on both these values, then you will get this alpha x and alpha y directly. So already I solved so many times how to make the interpolation for the two values. For example, if you will get any midterm value, how to make the interpolation by using some scale. For example, 1.1 it will be around 0.074, and for 1.2 it will be around 0.084. So what is the intermediate value for 1.14? Like that I showed each and every time in the beams and slabs. You please check once the procedure how I did. In the same way you can simplify these two also. For 1.14 how it will be. So I will take the values directly. So your alpha x value will be equal to 0.078 and alpha y value will be equal to 0.06. After that, take down in the formula, mx will be equal to moment in x direction, that is alpha w lx square, which was in the code book. Now I showed here 0.078 into w will be equal to how much it will be 11.625 into lx square will be so 3.625 whole square. So directly we will get the value of moment will be 11.92 kilonewton meter. Similarly in the y direction, moment in y will be equal to alpha y w lx square. So it will be around simplified, take down all the values. Alpha y will be 0.06, w will be equal to 11.625 into lx will be 3.625 whole square. It will be around 9.17 kilonewton meter. So here both moment in x direction and moment in y direction values will be obtained. So then I will check the depth. So what is the depth I taken is correct or not? It's suited to the particular problem or not? It will resist the bending moment or not? Like that I will check once. That is mu will be equal to 0.138 fck b into d square. Here d I am going to check here. Mu again there will be 2 mu. So I will go with higher moment. Why? Because whatever the depth we choose in, it will resist higher moment, means automatically it will resist this lower moment. If it is not put to the higher moment, means we can change the depth. Okay, then mu will be equal to 11.92 into 10 to the power of 6, that is 0.138 into fck will be 20, b will be 1000 for that is 1 unit meter into d square. So check the d, how much you will get? It will be around some 66 mm, which is less than what we adapted. So we adapted effective depth will be 125 mm, but here I choose somewhat higher value only. Why? Because it will also effective to resist the deflection control also. Therefore I choose an effective depth will be higher, that is 125 mm. So we are in safe side here. So check the effective depth once after obtaining the moments, and then provide the reinforcement. And for providing reinforcement, there will be two moment values, one in x direction moment in x direction and moment in y direction. So first I will go with moment in x direction value. Again I will take the same formula which was in page number 96 in IS code book. So I already shown that problem formula various times while solving previous problem. You go there and check that problem, that formula. I will show here also once. that is 1 minus Fi AST FCK into B into D. See in the code book where will in the annexure here G, that class 38.1, this formula I taken there directly. So always remember this formula directly. Then after taking this formula, simplify the values, what will be given. So already we have MUX value, which is 11.92 into 10 to the power of 6 and 0.87 into 415 into area of the steel, and D value what we chosen, and again 1 minus Fi will be 415 AST by FCK will be 20 into B value will be 1 unit, and again D value will be 125. So if you simplify by using your scientific calculators, your area of the steel will be around 277 mm square, I think 278.6 mm square. Okay, then provide spacing directly here itself. Further the formula will be AST will be AST by AST into 1000. So generally after opening the area of the steel in the beams, we are providing n number of bars, capital AST by small AST. Based on that we can provide n number of bars by taking a diameter as the trial. But here in the slabs you can provide whatever the value you are getting directly, and for that you can provide the bars. So we know that the condition in the Fe 415, the minimum diameter bar will be 8 mm, what we have to use for the slabs. So I will go with that bar only. Pi 8 square by 4 into the area of the steel obtained here is 276.8 into 1000. I will check the spacing, how much it will be. It will be around 181.6 mm. Then again we can check these spacing with other two conditions, that is how much the maximum spacing allowed, that is one will be 3D, another will be 300. Effective depth will be 125, which is 375 in mm. So out of these three you can choose lesser value, provide lesser value. So therefore provide 8 mm dia bars at I will take approximation of 180 mm center to center. Therefore area of the steel provided will be the value what we obtained directly here. And then next go with the movement in y direction. Again take down the same formula which was in code book page number 86, the same formula what we taken for movement in x direction. So this is the formula what we taken there, and again movement in y direction will be around 9.17 into 10 to the power of 6, 0.8, 415 area of the steel, D value will be 125. Sorry, here there will be one change while taking D value, so I will explain that value. So here D value will be taken lesser than the D what we obtained in the previous one. I will show that one. Here in the slabs you can see, you can observe one thing. So this is the depth of the slab, and again we provide the reinforcement like this in the y direction. Sorry, in the slabs generally we are providing reinforcement 8 bars, 8 dia bar in x direction. So x direction will be not like this, that is y direction. So this is x direction. I will choose 8 dia bars directly here. So this is the bar which consists of 8 dia, like that you can assume. Okay. So if I will cut this section, it will be like this. You will get only bar of 8 dia. In the y direction again we have to provide bars. In the y direction also, for example in the slab, this is a slab, we are providing reinforcement So this is the reinforcement what I provided here, and again in the y direction also we have to provide the reinforcement. So this is below, and the y direction what we are providing, upper top one. So like that you have to assume. If I see from this view, I will get one bar like this, another bar will be top like this. Here also the same situation happen. In the y direction bars comings like this. So what is effective depth? Effective depth taken for center of the bar to the top while calculating movement in x direction. But while calculating movement in y direction, again the effective depth will be taken from the center of the bar to the top. So for obtaining the center, you assume this diameter of the bar in y direction also 8 mm. Why? Because already we chosen 8 mm in the x direction, therefore I am assuming 8 mm. And from here to here again the center of the bar what we chosen. So here the center of the bar we are taking the length is from the center of the bar to the up to the another dia bar center. So I will omit that 8 meters. This is 4 and this is 4. Totally 8. So 125 minus 8 will be 117 mm. Again you understand one thing. The diameter of the bar will be taken from the top to the exactly at the center. So center means I am assuming 8 mm bar. From the top you just minus 8 also you will get directly. Otherwise you can remove this 4 and this 4. Like that also you can take. So here the corrected value will be 117 y direction. And again remaining values will be same. Here also FCK B value will be 1000, D value will be again 117. So this is the major correction what you have to remember while solving movement in y direction. Later you can check the area of the steel how much you will get directly by using your calculators. So here my area of the steel will be around 226.2 mm square. So after obtaining this area again go with this spacing, same procedure, small AST by capital AST into 1000. Small AST will be again I will go with the dia what I assumed first, 8 square by 4 into capital AST what obtained here 226.2 into 1000. So overall spacing will be 222.2 mm. Sorry, okay, the spacing will be around 222.2 mm. Again you can check with the two condition, maximum spacing allowed. One will be 3D, 3 into 117 mm, which is around 351 mm, and second condition will be 300 mm. So out of these three provide less value which is 220 mm approximately. So I will choose this value approximation. So here write down the statement, provide 8 mm dia bars at a spacing of 220 mm center to center. This is how the movement in y direction also. And I also tell one more point here. So movement in x direction and movement in y direction is also very near values. So here we are providing in x direction 8 mm bars. Here also we are providing 8 mm bars. But after calculation of all these things, what is the difference observing here? Here 180 mm spacing and here 220 mm spacing. So without calculation also you can choose the same spacing for this movement in y direction also it will be eligible, but we cannot choose this lower movement spacing for this problem. Why? Because here the moment is higher, therefore we can choose maximum bending moment spacing to the minimum also. So for making simpler to the calculation in the examination, you prefer which one will be higher, either in movement in x direction or y direction. You calculate movement for that one and then you can provide the spacing of the higher movement to the lower one also. Then your calculations will be simpler and accurate. Okay, then go to the next step, which is reinforcement in edge strip. So I will also explain what is edge strip and what is middle strip. So see in the code book, see here, this is how the diagram will be. So we can divide the slab for two-way slab, we can divide like this. In the x direction, see here in the x direction we are dividing Lx by 8 times, that is the edge strips. So we can remove the remaining part, we can remain like that only. So again in the y direction also your edge strip will be Ly by 8 times, So on a particular portion of the slab, we can divide like this. The edge positions will be around Lx by 8 and Ly by 8. Here also Lx by 8 and Ly by 8. Here also Lx by 8 and Ly by 8. Lx by 8 and Ly by 8. This is how the diagram will be. So the middle strip means we have to provide full reinforcement. Whatever the reinforcement we are taking here, it is 8 bars of 8 mm dia bars at spacing 180 mm in x direction. In y direction it will be spacing of 220 mm. In the y direction we are providing the spacing of 8 mm dia bars at spacing of 180 mm center to center. Why? Because the maximum bending moment happens at the mid span only. Therefore we have to provide maximum area of the steel at the mid span only. But at the edge strip actually it will be rest on the supports also. So therefore maximum bending moment also not happening at the edge strips. Therefore we have to provide minimum area of the steel. So that is the edge strip calculation. For that we have to provide just minimum area of the steel. So what is the formula for that one? So the formula will be that is area of the steel will be equal to 0.12% of gross cross sectional area. So that one will be equal to 0.12 by 100 into B value will be 1000, D will be capital, that is D value will be 115 mm. So if you simplify you will get the value that is 180 mm square. So this is the minimum area of the steel what we have to provide in the edge steel. So I am telling that this is the minimum area of the steel whatever required for this particular entire two-way slabs also. You can check once. So this is the minimum area of the steel what we have to provide in the edge strip, and this is the minimum area of the steel in the entire slab. So in the x direction the moment the area of the steel will be around some 276. In the area of the steel in y will be 222. If you check with these two, the moment will be higher only what we provided in the middle strip. Okay, so therefore our design will be safe. Otherwise if the moment in x and y direction will be some 150 and 160, at that time what we have to do means we have to provide minimum reinforcement in the entire slab also. We can't go with the minimum reinforcement if it will be gets lesser than this 180. So if your area of the steel will be higher than 180 means you can provide that one also what we did in this problem. So later you can check that condition also. So minimum area of this it will meets requirement of minimum reinforcement what is coming in this slab, that is 180 mm square. So we provided around 276 and 222 which is higher than the 180, therefore it is safe inside. And the reinforcement in edge strip is 180 mm square. For that you have to provide spacing, and again the spacing formula will be AST by capital AST into 100. So we know the minimum dia bar we using for the beams will slabs will be 8 only. 5 8 square by 4 into area of the steel will be around 180 mm square what obtained here into 1000. If you check this condition you will get around 279.3 mm. Again for the edge strip the condition will be different. Maximum spacing allowed one will be 5D, another will be 450 mm. So 5D means 5 into effective depth what we are taking which is 125, that is 625 mm. Another one will be 450. Out of these three provide lesser value. So in the edge strips we are providing the moment will be 8 mm dia bars, provide 8 mm dia bars at 270 mm center to center. I will take this as approximation, 270 mm center to center. So here calculating moment for the edge strips what we are providing here in this edge strips. For example here we are providing the bars like this, one bar will be like this and one bar will be like this. Each spacing will be 220 mm in y direction. But in the edge strip what we have to do, so in the same edge strip we have to provide the bars somewhat longer distance like 250 260. Otherwise you can provide the same reinforcement what we provide in the middle also, no problem. Why? Because but for the middle strip it will be must the spacing will be meets the criteria. But in the edge strip, whatever the moment obtained in the center, you can provide the same moment at the edges also, it will satisfy the given problem. This is how the reinforcement in edge strip. After that, you can go for the deflection. Check with the deflection. So we know that the deflection generally, and again one more deflection, one more check also we are doing in the slabs beams, that is shear. So how the shear calculations, tau v will be equal to vu by bd, but we are not calculating shear here. Why? Because slabs are almost safe in shear, so no need to check again once the shear reinforcement, it is almost safe in shear. So then go for the deflection check. L by d provided will be less than L by d maximum. Again, L by d maximum will be equal to L by d basic into only modification factor in tension reinforcement. You won't get compression and flange like beams. Okay, and what about L by d basic? It will be 20 for the simply supported slabs. And tension reinforcement, for providing the tension reinforcement, what we have to do, we can go with the page number code book. Again we can check the book, the tension reinforcement. So it will be around some 39, I think. So this is the graph for providing tension reinforcement. So see here, first find the curve. Fs will be equal to 0.58 into 415. What about the area of the steel required and provided? In the slabs, it will be both same. Why? Because whatever the area we are obtaining, the same area we are providing here. So therefore, required and provided will be same. It will get 1. So 0.58 into 415 will be 240 point some 7. Means we are taking curve approximately. So for 240 curve, I am choosing this curve, 240 curve. So this curve. And again, percentage of tension reinforcement will be PT will be equal to 100 AST by BD. So we know how much we are providing 100 AST. Pi diameter will be 8 square by 4 into 1000 into 125. If you simplify, you will get around this value will be some 0.223%. So 0.223 means somewhere here, you can check in the same line. Maybe it will meet exactly at here. So which is 1.6 factor. So already I shown so many times how to take this reinforcement problem. You please check there once. So 1.6. And at the same time, the modification factor here for slabs will be so simplify this one. 20 into 1.6 will be around 32. And again L by D provided, how much it will be? L value will be around 3625 in shorter span direction what we obtain, and D value will be 125. So if you simplify, how much you will get? It will be 29, which is less than 32. Therefore your deflection is also control, so safe. So deflection control is safe. Control is safe. So I already told you, this is the problem how to solve for the simply supported slab. Okay, and again, if they will ask some question like this, if the corners are prevented from lifting, means at that time we can go with another calculations. The questions will be coming like this: corners are prevented from lifting or discontinuous edges, means the edges are not continuous. So however the questions may be generally in the various steps they are giving. So at that time what we have to do means we have to provide torsion reinforcement. I have to provide torsion reinforcement. So now we are checking with that calculations torsion reinforcement for the same problem. Okay. So for providing the torsion reinforcement, we have to do. So further the calculations will be so torsion reinforcement. So for providing area of the steel, it will be 3 by 4 times of area of the steel in x direction. So 3 by 4 area of the steel in x direction will be, check the moment of area in x direction, we calculated, that is 276.8 mm. It will be around 207.6 mm square. So after obtaining the span, next step is check with the spacing how much it will be, that is small AST by capital AST into 1000. So small AST will be around pi. So for torsion reinforcement, if you want, you can take 8 dia. So I will choose here 6 bar, which is plain steel bar. Okay, then 4 into 207.6 mm square into 1000. So if you simplify, you will get around 136.127 mm. And again, for the torsion reinforcement, the distance is also required on the slab. So at what distance we have to provide? The distance will be 1 by 5 Lx by 5, which is 1 by 5 of the short span. Lx means short span direction 3625 by 5, which is 725 mm. So these are the requirement for providing torsion reinforcement for the simply supported beams. So I will explain that one. We have to provide. So generally this is a beam, sorry, this is a slab, this is a slab, both in x and y direction. So we are providing bars of both. From the top view I am showing here reinforcement in x direction and reinforcement in y direction in both spans, and again in the corners. So this is the mesh life. So I am providing 6 dia bars, 6 dia bars. So torsion reinforcement I am providing like this. So here check with condition, provide 6 mm bar, provide 6 mm bar dia bars at 130 mm. I am taking this as approximation, center to center. So and up to what distance? 725. So here I am providing the mesh like this. So this is torsion reinforcement in x direction, y direction. So each spacing will be 130. So how much distance we have to provide? So this is in x direction, and also we have to provide the same torsion reinforcement in y direction. Okay, see here, each and every spacing distance will be 130 mm and the diameter of the bar will be 6 mm. So the total distance is 725 mm. Like that, both in x and y direction, you can take short span length of overall 725 mm distance. In that, you have to choose 6 mm dia bars and 130 mm. So this is the torsion reinforcement. The same thing you have to provide at the corners like this, and that too in 4 layers. 4 layers means, so this torsion reinforcement will be provided in 4 layers. Means first you have to place this torsion reinforcement, and again you have to provide the bars, and again one more layer you have to provide this torsion reinforcement top side, bottom one, top one, like that. It will be totally 4 layers. This is 2 layers. First layer of one dia, second layer of another dia. This is totally consist of one unit, and again the same unit you can provide bottom side. So totally 1 2 3 4, like that you have to provide in 4 layers. This is totally 2 layers, and again 2 more layers will be provided on top of the bars. So finally from the top, if you can see like that, you have to provide torsion reinforcement. And again, already in the basic I will explain all the things. For example, if you see here, this is the simply supported edges will be discontinuous on all sides. We have to provide torsion reinforcement on all corners. For example, one edge it will be continuous like this. One edge it will be continuous. It will be continuous. At that time, you have to provide this full torsion reinforcement at this ends in 4 layers. But coming to here, you just provide 3 by 8 of area of the steel. Means you can calculate here 3 by 8 of area of the steel in x direction. So means we have to provide half of the reinforcement here. Similarly, here also you have to provide full reinforcement. Here 3 by 8 of the area of the steel. Here both 3 by 4 and 3 by 4 area of the steel we have to provide. But one more condition what I explained. Coming to the torsion reinforcement, if it will be two edges continuous means like this. So we have to provide torsion reinforcement at full reinforcement only at this edge, that is 3 by 4 area of the steel. Here you just provide 3 by 8 of area of the steel. Here also 3 by 8 of area of the steel. But here no torsion reinforcement is required because both edges will be continuous. So this is how the torsion reinforcement will be provided on the slabs. It comes under the discontinuous edges. Simply supported beam, you have to provide torsion reinforcement on all the corners. If it will be continuous edges means you have to provide torsion reinforcement on only specific corners. Okay. Then coming to the condition, the calculations will be different for the continuous edges. The calculations will be same for the simply supported conditions. Means whatever the problem we solve now, it will be purely related to the simply supported slabs. The corners are free to lift or prevented from lifting. But whenever continuous edges will be given like this, the procedure will be somewhat different while calculation of the movements. So I will discuss based on that point only. So here it will be totally different. The calculations will be somewhat, not totally. So I will cut this one and I will paste in the next one, and I will discuss only about the continuous edges. See in the code book, see in the see here in code book, that is page number 91, table number 26. Here it is clearly mentioned bending moment coefficients for rectangular panels supported on 4 sides with provision for torsion at corners. If you read the conditions, you will get a idea. So one short edge continuous, interior panels, one long edge discontinuous. One short edge continuous means this is a slab. So generally this is some 3 meters and this is 4 meters. One short edge continuous means, so this is short edge and it will be continuous here, another slab. So at that time what you have to do, the conditions will be taken based on this. So your Ly by Lx ratio, maybe you will get 1.14. Already we solved only simply supported beam like this. So if it will be simply supported, what we have to do means you can solve the problem based on this table number 27. So without continuous edges. But the problem will be like this if one edge will be continuous. And again one long edge discontinuous. So what is the condition here? One long edge discontinuous means only one long edge, there will be no continuation slab. Another 3 edges, 2 short edges and one long edge will be continuous. Means this long edge only free, which is y direction 4 meters, short span direction 3 meters. And again the same condition they will given like this also. 3 edges continuous, 3 edges continuous and one long edge discontinuous. Like that also they will given the conditions. So you see the condition. For example, if you observe this fifth one, 2 short edges discontinuous means 2 short edges, this is 3 meters, this is 4 meters. 2 short edges discontinuous means the long edges will be continuous. The same condition will be given like this, 2 long edges continuous. Then automatically you have to observe, assume that 2 short edges discontinuous. Like that the conditions will be differ here. And again, these are the Ly by Lx ratio values for finding alpha x up to from here to here. And these are the alpha y values for finding Ly by Lx ratio. For example, it will be 4 by 3 meters. How much you will get around? Check once in the calculators. 4 divided by 3 will be equal to around 1.33. So it will be 1.33 here. So where 1.33 lies? 1.33 lies between 1.3 and 1.4, means it between 1.33. So for M20 grade concrete, generally the concrete grade is not mentioned, just Ly by Lx ratio will be 1.33. So for finding alpha x, I will check with some discontinuous edges. Two adjacent edges discontinuous. So the value lies between 0.65 to 0.75. Maybe I will assume alpha x will be equal to some 0.67, because my value between 1.3 and 1.4. And again, that two negative moment at discontinuous edges, means moment x negative. Okay, here the formula alpha x WLX square. So you have to substitute the alpha x value will be this 0.67. And again, positive moment at midspan. So here also alpha x value lies between these two, which is 0.50. And again, moment x positive. So this is also x, this is also x, this is negative, this is positive. Alpha x value will be taken this one, WLX square. Similarly, there will be two more values. So this 0.07, 0.035. So this is alpha y value in negative, and again this is alpha y value in positive. So you can take down the formula mu y negative will be equal to alpha y WLX square. So you can take down this value directly 0.047 WLX square. Similarly for the next one 0.035, which is positive, mu positive equal to 0.035 WLX square. So this is the formula for finding. So in the previous problem, if you observe that only short edges continuous, means only you will get mu x in y one, mux moment one moment, and muy one moment. But here in the mux itself you will get two moments, positive moment at the continuous edge, and positive moment, negative moment at the continuous edge, and positive moment at midspan. And again in the y direction also you will get one negative moment and one positive moment. So at that time entire procedure remains same, but while solving reinforcement you get these four formulas moments. So you have to find out this mu x in negative, mu x in positive, and again mu y in positive, mu y in negative. Here also each and every one, for example, maybe you will get this one as some 10, this one has some, this one has some 12, this one has some 11.5. So you have to find the area of the steel for each and every problem. Here for higher moment you have to find the depth required. Why? Because it will resist the higher moment, automatically it will be resist for all the other moments also. Each and every moment you have to find the area of the steel and individually provide the bars. Otherwise you will do one thing, in the moment in positive direction, in the moment in x direction, you see which moment is higher and find out the area of the steel for that particular moment and provide the reinforcement for that to the other also. In the y direction also you can do like that only. So this is how the procedure will be different for the simply supported beams and the these beams. So if simply supported beams will be given, means you can solve the problem based on the this table, which was table number 27, already I solved. Now whenever a continuous edges will be given, means you can see here the conditions what it suited, and you can take down the values based on these conditions, and you can find out moments based on these conditions, and then area of the steel. After finding area of the steel, entire procedure remains same, but finally what you have to do, here in the simply supported edges we provided area of the steel for the, we provided area of the steel only for the, for all the corners. So I will check the condition where it will be. See here, torsion reinforcement will be provided for all the corners because it is simply supported slab which is resisting on all the corners. Means there is a chances of lifting the corners entire edge. Whenever continuous edges will be given, check the condition, find out the moments based on that particular condition as shown in the table number 26, and then you have to provide wherever torsion reinforcement is required. In this case, here you will get full torsion reinforcement, here you will get half of the torsion reinforcement in both the sides. Like this, the procedure will be different. Okay, how to provide the torsion reinforcement for if the edges will be continuous and if the edges will be discontinuous. So this is the procedure. And coming to the reinforcement details, so this is the simply supported beam what we solved now, simply supported slab. So what we solved now, see here, the simply supported slab, the overall length of the slab in shorter span direction will be 3650, in longer span direction will be around 4000, it will be around 4000 from here to here. Okay, so already I shown you in the code book, it will be divided the edge strip. So how edge strip, longer span direction means shorter span direction Lx by 8, longer span direction Ly by 8, middle 3 by 4 times of Ly, and again here Ly by 8. Like that you have to divide the panel. And again, so we know one condition, we are providing the bars like this, one bar will be cranked here and the crank distance will be 0.1 L. So here it will be 0.1 L, we have to take the crank distance. So this is 0.1 L. So one bar will be cranked one side, another bar will be cranked one side. So like that we have to provide bars in x direction. So already we know we choose 8 bars at 180 mm center to center in x direction. In the same way they are providing one more bar in the longer span direction with cranks. One alternate bars will be cranked here. See here, one bar will be bent this side, another bar will be bent this side. So this is how the bars will be provided in the longer span in the two-way slabs. In the one-way slab, they are providing only cranked bar in x direction and only distribution bars in y direction. But here in the two-way slabs, they are providing alternate bars cranked both in x direction and y direction. So here in the y direction, the diameter of the bars will be 8 and spacing will be 270 mm center to center. So what we resolved. And at the same time, if you see here, the bars, the distribution bars, these bars, if you see from side view, the bars will be visible like this continuously, this bar. So what the bar will be placed here, and again whatever the bars we are distribution in y direction, that will be appeared in round bars like this. And again, so whatever the bar cranked here, the bar will be cranked this side, and here the cranked bar, it will be visible this side. So for resisting the crank, we are providing the reinforcement bottom of the crank. So this is the these are the bars which are giving support to the cranked bars. So this is in the slab xx direction we are showing in the diagram. So this is the slab, how generally it will be. So this is the procedure how you give detailing of the bars. So the cranks will be around some 0.1 L. So this is the width of the column, see each and everything. Like that you have to divide edge strip, middle strip on both x and y direction, and again you have to stretch that bar, cut the section xx direction, and whatever the part seeing in front view you can provide the same in the section xx wise. And again I will show you the another procedure. Sometimes if you observe this bar in the two-way slabs, they will provide the bars like this also. This is the bar. Generally one bar will be provide like this and another wall will be cranks on both sides like this in one direction only. Again another bar will be leaving like this only, another bar will be cranked. So in the y direction also they are providing this like this, one bar will be cranked, means alternate bars cranking on both sides. See here, the bar will be cranked here. Again, one more bar, straight bar. So one bar will be cranked, one bar will be straight bar. Like that also you have to provide. So previous what I shown in the diagram will be like this. One bar will be cranked one side, another bar will be cranked on another side. Okay, this is how the difference of the bars, and at the same time we provided torsion reinforcement for another problem. So for that, how the torsion reinforcement will be differs. So see here, you can provide torsion reinforcement like this at all the edges. So here I will talk about this edge. We can provide the torsion reinforcement both top and bottom. For example, I will show you that image also. Whenever torsion reinforcement is provided, how it will be. See here in the diagram, I will show you one more diagram. See here, this is the torsion reinforcement provided in this slab. So see here, this is the torsion reinforcement. So supported edges. So this is only two layers, one bar, another bar. That is two layer. And again, bottom of the slab also they are provided. If you see in section XXY, you can observe clearly. This is the torsion reinforcement. What is clearly visible in the top bar. One bar will be upper. So like this. Again, in the bottom also they will provided bar and hooks. So this bar will be horizontal line will be this horizontal line only. This round dia bars will be in the section XXY. It will be observed like this. Here also it will be observed like this. So you can observe clearly after providing the torsion reinforcement, you will get in the side in the XX view like this, in the section XX view like this. So like this we have to provide torsion reinforcement for all the corners, but here in the image they are showing only once. Why? Because this is simply supported edge, you can provide torsion reinforcement. And what about this length? Already we calculated that length will be around some 725 mm both in X and Y direction. This is how the procedure will be different. If you provide torsion reinforcement means it will be like this. If you provide a general without torsion reinforcement means this will be like this general image. So if you provide torsion reinforcement, so the images will be like this, and at the same time cross sectional view XX view will be like this. Here also they are clearly showing that torsion reinforcement both top and bottom. So this is the different in the procedure how to provide the detailing of the reinforcement. Thank you so much for watching this video. If you really like this video, please like this video, share it to your friends and subscribe our channel. Thank you so much.